In the tropical heat of a Madagascan afternoon, the shade of the trees is a welcome relief. The going is tough through a dense jungle of mango, wild banana and palm, and the expedition makes slow progress, trailing machete-wielding guides. The year is 1860, and these remote forests have never before been seen by Western eyes. And what wonders there are. Plants, trees and animals completely unknown in Africa, just a few hundred kilometers to the west, let alone the rest of the world. Bloated baobabs, delicate orchids, and above all else, lemurs. As the exhausted party rest within the sweltering understory, a family of these curious animals clatters noisily through the canopy overhead, shrieking their alarm at the intruders below. Dense foliage hides the mammals from view, but a rare glimpse shows a long, black and white striped tail swung out for balance. Below, one of the Westerners wipes sweat from his brow as he hastily notes down the sighting. Another novel variety to add to his ever-growing list. By the end of that year, that wonder-struck adventurer had survived the voyage back to England. Presenting his sweat-stained notebook, along with several crates of samples, to the secretary at the Zoological Society, Philip Slater. Slater had made a name for himself in the realms of ornithology, proposing a new way to divide the globe, based on the distributions of birds. But, as with many of his fellow scholars of the Victorian age, his curiosity about the natural world could not be contained. And now he turned his attentions to the mammals of Madagascar. He pored over the specimens returned to him, probing and classifying with intense fervour. And slowly and surely, a seed of an idea grew inside his mind. There was indeed a staggering bounty of lemur species in Madagascar. Ring-tailed lemurs like the one glimpsed through the trees were joined by 29 other distinct types. Such variety for such an isolated island. In comparison, Africa boasted a mere 12 species, and the Indian subcontinent only 3. The implication could not have been clearer in Slater's mind. Madagascar had to be the primordial homeland of these tree-dwelling mammals, from which the Asian and African varieties were derived. But how had they crossed the great oceans between? Slater was once again confident in his conclusion. They must have travelled overland, across a land bridge that had once connected Asia, Madagascar and Africa. Such a bridge must have been gigantic in extent, occupying much of the western Indian Ocean. In fact, it would be more fitting to call it a continent. Slater named this hypothetical lost continent, the supposed connection that allowed lemurs to flow out of their homeland, Lemuria. At this point of the 19th century, the idea of lost continents was not such an outrageous one. As geologists strove to understand the rocks that painted the globe, they imagined ocean basins as sunken, drowned landmasses. Our continents today may have been raised, dripping from the seabed, producing marine fossils in unlikely inland locations. So, Slater's proposition of the sunken continent of Lemuria was a sensible, scientific supposition. But the following decades would see his ideas seized and transported outside the realms of science, and ultimately into the occult. In 1876, a new rejection of the theory of evolution was published by German zoologist Ernst Haeckel. His History of Creation not only rejected Darwin's suggestion that humans had evolved and radiated from Africa, preferring an Asian origin instead, but suggested it was Lemuria that the lost cradle of humanity could be found. For Haeckel, it was here, among the lemurs and the other lower primates, that mankind first emerged, spreading to Asia and Africa before the continents sank. In later translations of Haeckel's work, maps depicting Lemuria in the Indian Ocean were labelled Paradise. In the decades that followed, the idea was transformed yet further. For the Russian medium Helena Blavatsky, whose esoteric religious doctrine, Theosophy, was followed by 45,000 at its peak, including members of high society, Lemuria was the mythical homeland of one of the 7 races of humanity. A group of egg-laying hermaphrodites endowed with 4 arms and 4 eyes, who lived alongside dinosaurs on the lost continent until its fiery destructive end. The concept of Lemuria, from its well-intentioned scientific beginnings to its strange transcendence into the occult, was one that nevertheless persisted well into the 20th century. It wasn't until modern theories of plate tectonics came to the fore that the lost continent was finally sunk. And so, the last 60 years of geological and geophysical study have revealed an altogether more provable history of continental movements through time. Rather than merely rising or sinking, they traverse the globe, joining and splitting, building and shattering. Lemuria may never have existed, but we now glimpse an even more evocative past. There are generations of Earth's long-lost supercontinents waiting to be discovered. This video is sponsored by Magellan TV, the documentary streaming service. Magellan have been great supporters of the channel for a while now. They offer a vast range of programs on a truly comprehensive range of topics, more than 3,000 in total. From the depths of space to the dinosaurs, there's something here for everyone. Head over to History of the Universe to find out how they've inspired our work. And one Magellan doc that we enjoyed recently that pairs nicely with this video on supercontinents is Super Volcanoes, a fascinating exploration of what makes these Earth-shaping titans tick. And you can now take advantage of an exclusive offer, 30% off an annual membership. This gives you an entire year for less than $3.50 a month, even if you've joined Magellan before and lapsed. You can simply click on the link in the description to claim your discounted membership today. Towards the end of 1994, a small spacecraft plunged, whirling, into the scorching clouds of Venus. It was a graceful death, well deserved by a probe that had accomplished so much in its short life. For the last 4 years, the Magellan probe had been swooping past the shrouded planet in great polar loops, passing from north to south just 300 kilometers above the surface, before swinging far out back into space to prepare for another pass. With each transit, as the planet rotated serenely beneath its clouds, Magellan imaged a new swathe of the Venetian surface. But normal cameras would not suffice here. Earth's twisted neighbour is so thoroughly wrapped in cloud and haze that visible light cannot hope to penetrate. Instead, Magellan scanned the alien surface with radar, and in less than 2 years had mapped 98% of the surface in unprecedented detail. But the radar images revealed something strange. Venus seemed to have no continents at all. Despite being so similar to Earth in size and rocky composition, the swaddled planet seemed to have none of our surface diversity. Magellan saw plenty of volcanic features, from shield volcanoes to vast lava fields, but they were all hallmarks of a single basaltic rock. No sedimentary deltas, no metamorphic mountains, no explosive stratovolcanoes. Only dark, fluid lava over the planet's entire surface. Magellan's data was invaluable to scientists trying to understand how Venus became Earth's evil twin. The radar images revealed that the plate tectonics that define our surface never really played a role on Venus. Without the lateral movement and recycling of the crust, there was nothing driving the creation of new types of rock. Without a tectonically driven rock cycle and being positioned that much closer to the Sun than Earth, Venus's conditions spiraled out of control. Without plate tectonics, the planet was baked alive. Earth was dealt a luckier hand. The beginning of plate tectonics established a feedback cycle that has protected us from Venus's fate for the last 3.5 billion years. Those plate tectonics have also endowed our planet with a startling variety of rock types, and we can trace the first continents of all to those earliest creeping moments. Continental crust is special. It has a distinct and refined composition, like a fine whiskey to the raw grain mash of the oceanic crust. As plates collide, they crumple and thicken, allowing molten rocks to sit for longer in the heart of the crust. Here, they partially crystallize, losing their heavier minerals and becoming progressively lighter and less dense. It is these relatively lightweight granitic rocks that are the foundation of our continents. And they have been gradually accumulating ever since plate tectonics began. Because of their lower density, they float buoyantly on the top of the mantle and are not easily subducted at collisional plate boundaries. Instead, it is the denser, basaltic, oceanic crust that floats lower and is sacrificed at subduction zones. In this way, continents, once formed, stand proud, bubbling like a cork that won't be sunk. They can be destroyed, of course, by the forces of wind, water and ice, but in any clash of tectonic sumo, these bulky behemoths will always emerge victorious. The oldest remaining fragments of continental crust today are some 3.5 billion years old. They have persisted in the face of erosion, collision, and rifting. We know their great age from mineral crystals called zircons that are some of the most resilient constituents of continental rocks, and which contain a precise elemental clock in the form of decaying uranium atoms. By precisely measuring the proportions of original uranium and its decay product, lead, geologists can reconstruct the age of the crystal, and therefore the rock that contains it. Even after the original rock is eroded away, the zircons will survive, to be reincorporated into sedimentary rocks and preserve an echo of the mountain that gave them birth. In this way, tens of thousands of zircons have been dated to build a picture of continental crust creation through geological time. More zircons imply more rock formation, but the actual record seems to show a surprising pattern. There are times when zircon production is inexplicably low, when continents merely exist and are barely being added to at all. How does this fit with a global picture of plate tectonics? To understand that, we must take a step back from individual crystals and search for other clues in the continental fragments preserved on Earth today. In the 16th century, perhaps no one in the world had looked at Earth's continents quite as closely as Abraham Ortelius. Fascinated by the intricate process and artistry of committing vast swathes of land to a single sheet of paper, he pursued cartography with almost every waking moment. It is little wonder, then, that this influential geographer saw something in the shape of the world that none had given voice to before. The coasts of Europe, Africa, and the Americas seemed to match one another. Ortelius imagined these continents ripped apart, as he described it, by devastating earthquakes and floods. Arguably, he was the first to imagine the concept of continental drift, an idea which wouldn't truly be popularized until the early 20th century by the meteorologist Alfred Wegener. For it would be nearly 400 years before modern scientists could verify that the Dutchman's suppositions were, in fact, correct. Africa, Europe, and the Americas had indeed once been joined and had been torn apart by the inexorable forces of plate tectonics. Earthquake and flood was just the beginning of the catastrophe that befell these once united continents. As Ortelius contemplated the shapes of shorelines on his 53-page atlas of 1565, he was unknowingly tracing the open wound of a supercontinent, ripped asunder. There are no supercontinents on Earth today. The largest discrete landmass is Eurasia, with an area of around 55 million square kilometers. But even this gigantic continent makes up little more than a third of all the land area on Earth. Various definitions of supercontinents require that all or nearly all of the Earth's continental crust be gathered into a single, immense and unbroken landmass. Alternatively, some scientists accept a more loose definition, that a supercontinent is merely the joining of continents that had previously been separated. Yet still, whichever way we look at it, there are no supercontinents on Earth today. But there are clues, buried within the crust, that show that this hasn't always been the case. The young crust of ocean basins preserves one of the clearest histories of continental movement through time. Oceanic crust is produced at mid-ocean ridges, like the one in the center of the Atlantic, adding incrementally to the gigantic slabs either side at a pace of 2.5 centimeters per year. That's roughly the same speed as our fingernails grow. The great continents attached to these slabs are shifted by the same amount. So, by reversing this oceanic conveyor, we can travel back through time. And close the Atlantic, reuniting Europe and Africa with the Americas. Other ocean basins aren't always so easy to interpret, but geologists turn to the fossil compasses frozen in these rocks to reconstruct the time and direction of movement. As our magnetic field has periodically flip-flopped, swapping north and south magnetic poles every few million years, the reversals are recorded in the new crust that forms. Stripes of magnetic anomalies are etched invisibly into the crust, like data on an old videotape. Once again, we can play that tape and watch the continents dance. But ocean basins can only help us so far. Unlike continental crust, oceanic slabs are easily sacrificed to the mantle when two plates clash. And the constant production in one place on the globe inevitably means constant destruction elsewhere. The oldest ocean crust that survives today is just 340 million years old, in the Mediterranean Sea. That means there is still some 3 billion years of continental movement that we cannot hope to know from basins alone. For that, geologists must turn to the continents themselves. The landmasses preserve a history of where the rocks have travelled, as well as the trials they have faced through the years. The volcanic rocks that preserve fossil compasses are rare on the continents, and not regular enough to preserve the periodic reversals, but they can still be used to pinpoint the magnetic pole at the time of rock formation. If that rock has since rotated or moved east or west, then its fossil compass will be misaligned. Moving the rock and its associated landmass back, we can plot that continent's position at the moment the rock formed. And more traditional fossils offer a straightforward reconstruction of continental juxtaposition. If fossils of the same organism are found on now separated continents, we can assume that these landmasses were once connected somehow. By plotting the paleogeography of entire fossil communities, paleontologists can reconstruct not only the ancient continental configurations, but also the locations of these landmasses on the Earth. 300-million-year-old fossils of Glossopteris, a tall woody shrub with tongue-shaped leaves, are found in Antarctica, India, Australia, South Africa, and South America. Their distribution suggests that not only were these now disparate landmasses once united, but that the resulting supercontinent must have sat at temperate or tropical latitudes, where the wet, swampy conditions the plant preferred could dominate. The distribution of lemur-like animals across Africa, Madagascar and India today is not due to the sunken land bridge of Lemuria, but rather a sign that the three were once joined and have since been rent apart by lateral plate tectonics. Other clues in the surviving continents are harder to decode, but offer a window into the moments of continental collision and separation. When two buoyant landmasses collide, and neither is willing to succumb to subduction, the rocks crack, crumple, compress, and eventually come to rest. The resulting mountain chains can reach many miles higher than surrounding landscape, like the Himalayan range and Tibetan plateau today. And the rocks formed at their hearts preserve the tortured scars of the collision that formed them. And over millions of years, even the tallest mountain eventually succumbs to erosion, and the hearts of these ancient ranges are exposed at the surface. They are known as orogenic belts. Using these warped rocks to reconstruct mountain-building events many hundreds of millions of years in the past is not straightforward. But doing so reveals precisely which continental slabs collided and when. Yet, even if we don't fully know why, we now have a clearer picture than ever of our planet's checkered supercontinental past. Scotland and England are now as one, fused together at the northern edge of the Eurasian continent. But this was not always the case. 500 million years ago, they were separated by a great ocean, the Iapetus. But plate tectonics is ever fickle, and driven by the unpredictable flows of the upper mantle, gradually the Iapetus Ocean basin began to close. The continent of Laurentia, along with the Scottish homeland, bore down upon Baltica and what was to become England. When all of the ocean basin was gone, the two Leviathan continents crashed into one another, building mountains in an event known as the Caledonian Orogeny, and fusing the Laurentian and Baltican continents together forever. By 420 million years ago, in the Silurian period, when life had barely made it onto the land, the Iapetus Ocean was no more. And all that remained was the twisted crash site of two continents forced unforgivingly together. That crumpled mountain range has since eroded. But geologists can still trace the tortured scars across the British landscape. The Iapetus suture zone runs from the Solway Firth to Lindisfarne, uncannily close to the modern Scottish border. The Iapetus suture is just one of the scars left behind in ancient continental crust. There are collision zones like it all over the world, but as we probe further back in time, crustal clues that have escaped erosion become increasingly hard to find. Some of the oldest remnants of continents, called cratons, can be found in Canada, Australia, South Africa, and elsewhere today. But there are tantalizing hints that, in their earliest days, they were united into one or a series of Archean supercontinents. One reconstruction extends the record of supercontinents almost back to the first continental masses of all. A single early supercontinent, has been proposed based on the observation that all of the cratons dating to 3 billion years ago were clustered together at a later time, so are likely to have formed and stayed together since their earliest moments. But with such ancient rocks, few other clues remain that could hint at the configuration or position of and its very existence relies on a great number of assumptions. Instead, a more conservative reassembly suggests that the ancient cratons were incorporated into a series of continents that formed and reformed throughout the Archean and into the early Proterozoic. The first was Valbara, which reigned from around 3.4 to 2.7 billion years ago, and combined the Kap Val craton, now found in South Africa, and the Pilbara craton of Australia. Next came the continent known as Superior, which existed from 2.7 to 2.3 billion years ago, and of which only the Canadian Superior craton survives today. At the same time, the Slavia continent, including the modern Canadian Slave craton, reigned from 2.6 to roughly 2 billion years ago. These reconstructions are based on the scant ancient evidence available from these and other crustal blocks, including the pulses in zircon creation that are consistent with their assembly. But we have no real way of knowing where they existed on the surface of the Earth. Some have even suggested that they were all united as far separated parts of a single, long-lived supercontinent called Kenorland, whose central regions have since been lost to time. If we could speed the geological clock from the early Proterozoic to today, we would be able to see the continental dance for what it really is. Individual landmasses grow slightly, but mostly they pivot, slide and link along oceanic distances. Sometimes the dances are spread far apart, and sometimes they linger, locked in an embrace. Those close holds represent the fleeting tenures of supercontinents, and the dance is punctuated by their calm motions before the continents whirl away once more. The supercontinent known as Columbia assembled around 1.8 billion years ago from crustal blocks that would later form parts of North America, Greenland and Europe. It was nearly 13,000 kilometers north to south and likely straddled the equator, favouring the northern hemisphere. Different interpretations of the orogenic belts left behind from that time produce very different reconstructions of these continental fragments. One suggests that pieces of Antarctica and Australia lay along the North American west coast, while an alternative places India in the same position. Geological evidence suggests that the Columbian supercontinent persisted until around 1 billion years ago, possibly contributing to a period of unprecedented environmental stability, known affectionately as the Boring Billion. At the end of its tenure, new rifts formed and new continents tore away. Next came Rodinia. Proposed timings for Rodinia assembly actually overlap with the breakup of Columbia. So it is possible that continents fleeing one superassembly were soon caught in the grip of another. But, as for Columbia before it, reconstructions are notable for their lack of agreement. At this significantly younger age, there are many more rocks available for comparison, but they are still disparate and much altered by time. Most geologists agree that the North American crustal block known as Laurentia formed the core of Rodinia, with Eastern Europe, Amazonia and West Africa to the southeast, and Australia, India and Antarctica to the northeast. Fragments of crust that now form the eastern part of Brazil were attached to the south. But the positions of ancient portions of China and Siberia are still the subject of debate. To further complicate matters, as well as overlapping with Columbia's breakup, Rodinia assembly may have been concurrent with its own destruction. Like some vast and ponderous Newton's cradle, continents crashed into the scrum, even as others broke free. The Proterozoic Earth's surface was cluttered with cratons as Rodinia broke up between 850 and 600 million years ago. Some passed briefly across the South Pole, colliding as they approached from different directions, as Rodinia turned itself inside out across the globe. The resulting supercontinent, Pannotia, saw the Congo craton amalgamated with Laurentia and other Rodinian fragments. But the union was not to last. Even as the final sutures were healed around the edges, Pannotia began to rift apart from the middle as a new ocean basin, the Iapetus, appeared and began to widen. The very existence of Pannotia is far from certain, as the messy breakup of Rodinia is difficult to reconstruct across the Precambrian-Cambrian boundary. But the next, or possibly concurrent continental amalgamation is much better constrained. Gondwana may only be considered a supercontinent under one of the term's looser definitions, as several ancient cratons were excluded from its embrace. And yet, this landmass, which began its assembly with the chaotic destruction of Rodinia and was only completed at the very end of the Proterozoic, did represent the largest single piece of continental crust throughout the Paleozoic. Covering an area of around 100 million square kilometers, it saw 2/3 of today's continental area united, including cratons from modern-day India, Africa, South America, Antarctica, Australia, and Arabia. This supercontinent was a melting pot of ancient landmasses and was crisscrossed by orogenic belts, each marking a collision, a lost ocean, a continental fusion. The origin of Gondwana was a brief, calm moment after the continental chaos of the late Proterozoic. For a few 100 million years, there were no more collisions, and the supercontinent drifted gently northwards, until it eventually met its end 335 million years ago. Unlike those that came before it, Gondwana did not die through shattering rifts and diverging fragments. Rather, it lost its supercontinental identity as it collided with the now combined Laurentia and Baltica. It was assimilated into a greater whole, a supercontinent in even the strictest sense. The last supercontinent, Pangaea. Where there was naught but disagreement about the configurations of previous supercontinents, in Pangaea there is a wealth of supporting and corroborating evidence. There are plenty of rocks from its Mesozoic tenure, including fossils that can be mapped across once and future fragments, consistent magnetic anomalies, and unaltered orogenic belts. Pangaea, with its Gondwanan southern regions, reigned until 180 million years ago. The breakup of this vast and resplendent supercontinent saw the opening of the Atlantic Ocean, the migration of India towards the Asian subcontinent, and the utter isolation of Australia and Antarctica. And so, we find our modern world, formed from the scattered fragments of Pangaea, but also of Gondwana, Pannotia, Rodinia, Columbia, and maybe even Kenorland and Ur. Each supercontinental age was distinct in configuration, duration, climate, and character. Pangaea was covered in great forests, while Rodinia was barely greened at the edges. Pannotia was a frozen wasteland, while Columbia baked in endless deserts. Yet despite their differences, there are certain conditions that all of these supercontinents shared, and which life may face in the coming supercontinental age. Alexander von Humboldt was driven by an insatiable curiosity for the world around him. The German scholar travelled extensively through the Americas and Russia, seeking to learn the secrets of those often harsh but exotic lands. Wherever he travelled, he erected weather stations to measure the air temperature, pressure, and rainfall, and he collected data whenever he could to build a picture of weather variations over time and space. By 1830, he had collected enough data to map out those conditions over a huge swathe of Western Europe and Russia. Von Humboldt was the first to see clearly in his data what any Siberian nomad could have told him. The further inland you travel, the more extreme the weather would become. Winters in the interior were colder, and summers were hotter than in coastal places at the same latitude. This so-called continentality is a feature of all large landmasses on Earth today, and is more pronounced the larger the continent. For instance, Antwerp, close to the North Sea in northern Belgium, experiences an average summer to winter temperature range of nearly 15 degrees Celsius. Meanwhile, Saratov, deep in central Russia, sits at the same latitude but is some 2,000 kilometers from the nearest ocean. Its average temperature range is more than double that of Antwerp. These extreme conditions arise from the differences in how land and sea absorb the heat from the sun. In summer, land areas heat up much more quickly than the ocean, which can distribute its heat at depth. Whereas in winter, the oceans still have some store of heat left over to create milder conditions, while the land cools much more quickly. Coastal regions reap the benefits of the ocean, and the continental interiors are left out in the cold, or the heat. And it is not only temperature that defines continentality. Any satellite image of Earth today will reveal that the deep hearts of continents are often deprived of the green of life. They are deserts, where little rain falls and living things struggle to survive. One reason for this is the sheer distance. Rain is ultimately derived from warm oceans, and the greater the distance from those oceans, the less rain that is left to fall. But the clouds and life-giving rain are also blocked by mountain chains. The warm, moist air is forced up steep mountain slopes, where it cools, condenses, and rains out. The resulting rain shadow mirrors the real shadow of the mountain, but can extend much further inland. If such extreme conditions are to be found inside the modest continental landmasses on Earth today, then we can only begin to imagine the supercontinentality that held sway in the interiors of Pangaea, or Rodinia, or Ur. Supercontinents positioned at low latitudes close to the equator would see their central regions transformed into baked, dusty deserts, where not a drop of rain would fall for centuries, or even millennia. Even for the likes of Pannotia, straddling the South Pole, ice caps would be slow to grow if the snow that fed them never arrived. The suturing of crustal fragments during the assembly of supercontinents also generated mountains in staggering abundance. With every continental collision, huge ranges and plateaus to rival the Himalayas and Tibet are heaved out of the tortured ground. Monumental, towering belts stop weather in its tracks, creating rain shadows that bring the desert ever closer to the coasts. With vast mountain ranges creating a high-altitude labyrinth of blockages and diversions, wind and weather is whipped into a frenzy. High-level plateaus pump warmth and moisture into the upper atmosphere, driving monsoons that sweep their devastation across the coastal landscapes with terrible regularity. Flash floods and ephemeral rivers from these violent storms create huge inland deltas that irrigate the arid lowlands for a time. But these same winds, now stripped of their moisture, howl across the featureless deserts, sending dust storms tumbling viciously for thousands of kilometers. Such harsh conditions in the centers of most of Earth's supercontinents would have been little concern for life, since living things only began to colonize the land surfaces of Gondwana and Pangaea. But for those pioneering forests, insects, and teetering tetrapods, supercontinental life was unforgiving. Many places were all but uninhabitable. The dry interior deserts, the wild, wind-whipped mountaintops. But towards the coasts, and along sustaining rivers and deltas, the supercontinents offered a bounty of newly exposed mineral nutrients, and all living things thrived. Populations on land boomed and crashed with the march of the seasons, compared to the constancy of life beneath the waves. But there was plenty of time to adapt. The dance of the continents may seem frantic when we fast forward through Earth's history, but the reign of Pangaea spanned the entire ancestry of the dinosaurs, from the first slithering steps onto land in the Devonian to the mighty, long-necked lizards of the Jurassic. We cannot truly know what it is to live on a supercontinent, since that is not something humans have ever experienced, even in genetic memory. And unless humankind persists for another 250 million years or so, we may never know. We are living through a time of continental dispersion, but another supercontinental age is on the horizon. Even now, the assembly is beginning. The current movements of the plates will bring continents together, one by one. Africa and Arabia will grind northwards into Europe, closing the Mediterranean and creating a mountain range in its place. Australia and Antarctica will collide at high latitudes and may soon creep north together. Eventually, the Atlantic will stop widening and its crust will begin to be subducted. North and South America will rotate towards each other as they bear down on the Afro-Eurasian amalgamation. And as the North Atlantic disappears, the Indo-Atlantic is trapped as a huge inland sea between South America, India and Southeast Asia. When the collisions are finally concluded, 250 million years from now, perhaps all of the modern landmass will be combined into one immense supercontinent. Pangaea Ultima. Like the generations of supercontinents before it, Pangaea Ultima will be built from the shattered remains of its ancestors, but will have a character all of its own. For a biosphere like ours, now so thoroughly wedded to our continental land, it is hard to say whether such unity will be a blessing or a curse. You've been watching the entire history of the Earth. Don't forget to like and subscribe, and leave a comment to let us know what you think. Thanks for watching, and we'll see you next time.